Okay, so I think it has started recording. So, okay, so good. Welcome to the first lecture, the first class of MA524 Algebraic Number Theory. So we had this organizing meeting, so to say, the discussion meeting. We met last week for an hour or so, and I must have told you that this is a slightly advanced course. So you should pay attention from starting if you intend to continue in the course. Yeah. Okay. So today we will start the class, and today we will so I said last time that we might start with, so we will follow Lang's algebraic number theory. That will be the textbook for the course. And I told you last time that we might start with chapter 2 a little bit and then go to chapter 1 and then continue. So that's what we will do today. Let me start sharing the screen. One of you can confirm that this is visible? It is, no?
Yes, sir, it is visible.
Okay, good. So let's start lecture 1 of the course. And so here I have put some names here. So I will give. So what I mean is these names will come in the course in the lecture today. So Artin stands for Emil Artin, a very famous mathematician of the last century. Vapels stands for George Vapels. So there's a result due to Artin and Vapels, which we will see. We will actually prove it today. Then I will state two lemmas, one due to Hensel, Kurt Hensel, a very famous mathematician. In fact, he is the one who introduced the p-adic fields. I mentioned p-adic fields last time. He is the one who introduced it, and also Mark Krasner. So these names we will come. So these two I will state today, but we will prove it only in the next class. This result I will try to give a proof today itself. But before that, we will start with more basic things. So please feel free to stop me and ask questions. I welcome interruptions. And another thing is, if you put a question in the chat, I will not see it because I am not in the MS Teams window. I am in another window. I will not see the chats. So please don't put anything in the chats. Ask me directly. Yeah, unmute and ask me if you have any question. Or if you find any mistake or something, do point out and I will correct it after the class. Okay, so let's start. So once again, welcome to the first lecture of algebraic number theory, this elective. We will mostly follow the book Algebraic Number Theory written by Serge Lang. You must have heard about Serge Lang already, right? Can someone make a quick comment?
Yeah. Yes, sir.
Yes, sir.
Must have used his books for various courses. Is that correct?
Yes,
Yes,
sir.
sir.
Yeah. Be a bit more talkative, at least in the beginning. So you must have seen various books by him. He has authored so many books. A very famous mathematician. Passed away not that long ago, 2005, was a French-American mathematician born in France. Most of his working life he was in the US. And a very famous mathematician, many wonderful results in number theory and in geometry and in various areas. And most of us also know him because he has authored a lot of books. In fact, I counted on Wikipedia. There are some 60 books there, and I avoided repetition, second edition, etc. And I also avoided non-mathematical books. So still there are more than 40. So most of his books are very, very famous. He has books on all areas of mathematics, so there are more than 40 mathematics books. This book is also quite famous, Algebraic Number Theory. It's a textbook. It's also referred in research papers. It's also a very good reference. So we will do a first few initial chapters, maybe 1, 2, 3, 4. I don't know how much we can do. For electives, typically I will not have any rigid goal. Wherever we reach. That's all. Okay. We will start with chapter 2 and we'll go to chapter 1 later. These are slightly independent chapters. So we'll start with this. So the first notion is the notion of an absolute value, which you already know. So let's recall. Let K be any field, and an absolute value on K is a function which is real valued. In fact, non-negative reals. So K to R is a function on K valued in real numbers, and we denote it by mod X, and it satisfies some conditions which you know. So let's recall that it's always non-negative. Mod X is always greater than or equal to 0. And when is it 0? It is 0 precisely when X equal to 0. So if you take a non-zero number from your field, non-zero element from your field, it has a positive absolute value. It is 0 precisely when the element itself is 0. And then it's multiplicative. If you take the product xy and take the absolute value, it is the product of the absolute value. So absolute value of the product is product of the absolute values. And what is the third condition? The famous triangle inequality. Mod x plus y is less than or equal to mod x plus mod y. So this is true for all x and y in your field. Okay. So this is what is called an absolute value. And the most famous example is in Q or in real numbers, you have the standard absolute value, the usual distance, right? The distance from the origin, that's the standard absolute value. Instead of triangle inequality, sometimes it may satisfy a stronger inequality, and that's what I'm going to write now. So let's say 3 prime or something. Instead of mod x plus y is less than or equal to mod x plus mod y, sometimes your absolute value may satisfy this inequality. Mod x plus y is less than or equal to the maximum of mod x mod y. So if this is stronger, right? Because if this is satisfied, then of course this is satisfied. 3 does not imply this one, but this certainly implies 3. Because mod x is less than or equal to mod x plus mod y is less than or equal to mod x plus mod y. So sometimes the stronger inequality may be satisfied, in which case we say that the absolute value is non-Archimedean, right? Real numbers is an Archimedean field where this is satisfied and this stronger one is not satisfied. If the absolute value satisfies a stronger triangle inequality, some people say this is an ultrametric inequality. Okay, anyway, we say that it's non-Archimedean. Okay. Yeah.
So, like if you put y equal to 0 over here, you just get that x is equal to 0. Like suppose there is some absolute value which is non-Archimedean. You put y equal to 0 over here.
1 second.
And you get that mod x is less than or equal to 0.
So who is this asking? Manav? Yeah. What is the comment, Manav? Say that again.
Y equal to 0.
Where?
In the stronger inequality.
This one?
Yes.
Okay.
It's max there.
When you get that mod x is, oh sorry.
It's a max.
It's max.
So this is true for all x and y. So if y equal to 0, you will get maximum of mod x and 0. So you will get mod x equal to mod x. Okay, no? Manav?
Yes.
Yeah. By the way, since you said something, let me ask you, let's go a bit slow at the starting. Is there anyone who has seen this kind of a super inequality, ultrametric inequality? Or this is the first time that you see this? Manav, have you seen this before? Maybe you have to increase your volume. It's not that clear.
No.
Okay. Now this is good. So put the volume in maximum. Someone else has seen this somewhere, Preetham?
No, sir.
Okay, fine. But the inequality is clear, right? what this means is clear, right? So, okay, so maybe it's good to have, so I don't have many examples in the slide. It's good to have an example in mind. So okay, at the end of this slide, let us give one example. I'll quickly say it, and at the end, maybe I'll stop a bit before our time ends, and then we can discuss. Okay, so this is said to be non-Archimedean. So there is, of course, the trivial absolute value. So what is the trivial absolute value? There is, of course, whatever structure that we study, there will always be a trivial example. So you want to take a guess? So if x is 0, then mod x has to be 0. So on 0, you define the function to be 0. And at all other places, you define it to be 1. Of course, that satisfies all these conditions, right? So if x is 0, the answer is 0. Otherwise, you declare it to be 1. So condition 1 is satisfied. Condition 2 is satisfied because left hand side is 1, right hand side is 1 times 1. Condition 3 is also satisfied because this is 1 and here you will get 1 plus 1 equal to 2. So 1 is less than or equal to 2. And in fact, this itself is satisfied because the maximum of 1 and 1 or 1 or 0, which is 1, and this is also 1. So that is an example of a non-Archimedean absolute, but it is trivial. Okay, we will not discuss this. So this is a trivial absolute value. And once you have an absolute value, you have a topology, right? That's clear, no? Because if you have an absolute value, you can put a distance. What will be the distance of d of x comma y? How will you define it?
Mod of x minus y.
Mod of x minus y. Therefore, you have got a metric and therefore you have got a topology. Suppose you take this trivial absolute value. What is the corresponding topology? So once again, the trivial absolute value is at 0, the answer is 0. Everywhere else, it is 1. So what will be the metric?
Discrete metric.
What will be the metric?
Discrete metric.
Yeah, so the metric will be d of x comma y is 1 if x not equal to y and 0 when x equal to y. And what are the open sets in this topology? Every singleton is open. So it is the trivial topology. It's a discrete topology. Okay, we will not discuss this. It's too trivial an example. We will always assume that all our absolute values are non-trivial. So I will not say it again and again. Take a non-trivial absolute value. I will just say take an absolute value. I mean a non-trivial absolute value. Okay, that's the first point. I hope it's clear. In many of our proofs, it will be important that you are dealing with a non-trivial absolute value. And I will not stress this word non-trivial. It's understood. Okay, clear? Yeah, so I said maybe you should have a non-trivial example of this thing, and this is what is called. I mean, there are so many examples, but one very basic example is what is called the p-adic absolute value. So I don't have it in my slides right now, so maybe we can just discuss it here. So what you do is take a prime number p, and I'm going to define it on Q. Okay, on rational numbers, I'm going to define an absolute value. So if you take an integer, you know that it has prime factorization, right? So you can write it as a power of this. So you're fixing a prime p. So you have a prime p which is fixed, and any integer you can write as a power of this p times something which is coprime to p, right? That power of p could be 0. I mean, p may not divide your number. So you can write p power some 0 or some natural number times something which is coprime to p, and you define its absolute value to be. So if p power r times m is your number, you define its absolute value to be 1 by p power r. Is the definition clear? How am I defining it on integers? You define it to be 1 by p power r. Same if it's a rational number. So if it's a rational number, again you can write it as p power r times m by n, where m and n are coprime to p, but now the power r could be a negative integer also. Doesn't matter, you define the absolute value of that number to be 1 by p power r. Okay, so I leave it for you to check that it satisfies all these conditions plus this condition actually. It has a property that it satisfies this condition. So here is an example of a non-trivial, non-Archimedean absolute value. Okay, and what is called p-adic numbers is, so Q with respect to this absolute value you complete it. So this is you can show that this is not a complete metric space Q with respect to this absolute value. You complete it with respect to that metric, and what you get is the field of p-adic numbers. And you can extend this absolute value to the field of p-adic numbers also. Yeah, is there a question? Is there a question?
Sir, will the completion generally be a field?
You can check that, right? So if x and y are from your completion, then x is limit of xn, where xn's are from your starting place, and y is limit of yn, and you have to define x plus y as limit of xn plus yn, etc. So that will be a field. Similarly, all other things, and then you check that so it's a good question. So you check that it is indeed a field. Okay. So in the usual absolute value, when you complete, what you get is by definition the field of real numbers, and with respect to the p-adic absolute value, when you complete, by definition what you get is a field of p-adic numbers. So Nitesh, you should check this. Not just Nitesh, everybody should check that it is indeed a field. Okay, so let's continue. So I have given you at least one example verbally, and I have left something to be checked. Let's continue. So two absolute values are said to be dependent if they generate the same topology, right? Absolute value gives you a metric and metric gives you a topology. What is the meaning of same topology? Same collection of open sets. Actually the same collection of open sets. You may have two absolute values, but if they generate the same topology, then they are we say dependent. Some people say equivalent. I use the term equivalent for something slightly different, so it will come later. So let's say dependent. This is Lang's terminology. Definition is clear. They generate the same topology. Now I leave it as an exercise for you to check that two absolute values are dependent if and only if one is a positive power of the other. So suppose you have two absolute values, mod 1 and mod 2. Then they generate the same topology if and only if there is a lambda, which is a positive real number, such that mod 1 is mod 2 power lambda. What is the meaning of mod 1 is mod 2 power lambda? That means mod 1 of x is mod 2 of x power lambda for all x in your field. The same lambda works for all x. So this I leave it as a small exercise. So if and only if it has two parts, if mod 1 and mod 2 are absolute values such that one is positive power of the other, then they are dependent. They generate the same topology. This is clear, no? There's nothing to prove, right? Is this obvious? Suppose this is given to you that mod 1 is mod 2 power lambda. Is it clear that they generate the same topology? For example, consider open balls. Consider balls around 0, like mod 1 less than 1. Right? That will be the open unit ball in the first one. And that means mod 2 power lambda is less than 1. That means mod 2 is also less than 1. Or if you take mod 1 is less than r, you will get mod 2 is less than r power 1 by lambda. That's another ball. So open sets are open sets. Open sets remain open sets. It will have the same collection of open sets. So one way is obvious, and the other way you need to do something. So conversely, if mod 1 and mod 2 are absolute values which are dependent, what is given to you is there are these two absolute values, and it is given to you that they generate the same topology. You have to show that there is a lambda positive such that mod 1 is mod 2 power lambda. This requires a little bit of work. You will crucially use the fact that these are non-trivial absolute values. Try doing this yourself. If you don't get it, you can check Lang. Lang gives a proof. Okay, but don't look at Lang directly. Try doing this yourself. Okay, I hope this is clear. One way is obvious. The other way, it's not all that obvious because they generate the same topology. From that, you are going to say that there is one lambda which works for all x. So there is a little bit of work to be done, very little, not very difficult. So you have to do that. One direction is obvious. The other direction, in fact, you are going to prove the following statement. If mod x1 is less than 1 implies mod x2 is less than 1. If this is true, what is the meaning of this? If this is true, then what do you conclude? If mod x1 less than 1 automatically gives you mod x2 is less than 1, that means the open unit ball here is contained in the open unit ball here, right? What that means is the open unit ball in the second topology is open in the first topology. That's the meaning of this. The open unit ball in the second topology is also open in the first topology. So what you're going to prove is if this condition is there, then there is a lambda such that mod 1 is mod 2 power lambda. This is what you should prove. And if they generate the same topology, then of course you get this, and therefore this is true. Right? Generating the same topology is also same as saying they have the same convergence sequences. Right? This is the equivalence in metric spaces, metric equivalence of metrics. Okay, so this is what you should prove. So this I'm leaving. I'm not giving a proof right now.
Sir, one doubt,
Yeah.
sir. So,
Yeah.
so if we have the usual norm on Q, where it is just the mod of the value.
Yeah.
In that case, if we take like that mod square, that will not be a norm, right?
Very good point. Very good point. So I'm never asserting that. See, look at my sentences are carefully written. What I'm saying is two absolute values are dependent if and only if one is a positive power of the other. If mod 1 and mod 2 are absolute values, they are given to be absolute values such that this is true. Then they are dependent. I'm not saying that mod power lambda is an absolute value.
Okay, sir.
If mod 2 is an absolute value, mod 1 is also an absolute value such that this relation is true, then we are saying something. Okay. Conversely, if mod 1 and mod 2 are absolute values which are dependent, then they differ by a power. Some lambda. Okay, so very good point. I'm happy you said it. That's exactly my next statement. A positive power of an Archimedean absolute value need not be an absolute value. This is the example that you gave. Mod square you took. So what you can check is you may have to take that power. You may get the power also in absolute value, but you may have to take a small power if it is Archimedean, because you took the usual absolute value, right? That's an Archimedean absolute value. What you can show is, see, the problem comes only in triangle inequality, no? Nothing else is the problem.
Yes, sir.
Your problem came exactly here. May I know who's speaking?
Pradyumna, sir.
Pradyumna. So Pradyumna, the problem comes exactly here. But if you had the stronger inequality, then there's no problem, right? Any power is an absolute value.
Yes, sir. No problem.
Yeah. So non-Archimedean, there's no problem. Mod power lambda for any lambda is also an absolute value. But for Archimedean, your example will work, and therefore, there is this note that a positive power need not be. But I have phrased it properly here. It doesn't matter. Okay, good, very good. So continue speaking in between. Continue asking things. It clarifies things for everybody, including for me. Okay, good. So what is the point of this slide? The point of this slide is you have something to check after the class. Okay. And I'm stressing this, I have put this in italics as in quote form because I'm going to use this crucially, very crucially, I'm going to use this statement in the proof of Artin-Vapels. Okay, so this particular statement, if mod x1 less than 1 implies mod x2 less than 1 for all x, if this is true, then there is a lambda such that they differ by a positive power. Okay, so remember that there is this statement. Now let's discuss norms. So all of you know what a norm is. Norm on a vector space. Norm on a vector space is exactly these conditions, right? Exactly these conditions. Only thing is you have a vector space. So x and y are vectors. And this condition is exactly the same. This also is exactly the same. How will you interpret this now? If you are in a vector space over a field, you will say that y is a vector and x is a scalar. Then xy is a vector. Norm of that vector is the modulus of the absolute value times norm of the vector, right? Except for that change, it's exactly these conditions. So all of you know what norm is. You had functional analysis already. So recall the definition of a norm. And you may have an ultrametric norm where triangle inequality will be replaced by this other inequality, that norm of x plus y is less than or equal to maximum of norm x comma norm y. Now we say that that's why I used the word dependent earlier, because I want to define equivalence of two norms. It's something that you must have seen. if each one is less than or equal to a positive constant times the other. So if you have norm 1 and norm 2, they are equivalent. If norm x1 is less than or equal to a constant times norm x2 for all x, some constant, and norm x2 is less than or equal to some constant times norm x1. Each one is less than or equal to a positive constant times other, then they are equivalent. It's easy to show that. This is a bit more than the earlier dependence, right? This equivalence will give dependence, but not the other way usually. And in this case also you can show that they will generate the same topology, they will have the same convergence sequences, they will have the same Cauchy sequences, which is not true in the usual equivalence of metrics. Cauchiness need not be preserved. But in this, so this is what, for example, Wikipedia calls strong equivalence. When earlier thing, if you call equivalence, this is called strong equivalence. But we are calling this equivalent. Okay. So now let's make an observation. So let K be a field which is complete with respect to an absolute value. So you can take R, you can take QP, the field of p-adic numbers. These are all complete by definition, right? Because you're putting some absolute value and you are completing it with respect to that absolute value. Therefore, they are complete. And then you extend the absolute value also. So if x is limit xn, you define mod x as limit of mod xn. And you can show that that's well defined. So let V be a finite dimensional vector space over K. It's finite dimensional. And the first observation is that all norms on V are equivalent. So how is this norm on V depending on the absolute value on K? Norm on V is depending. So norm on V is depending on this absolute value on K, because in the second condition it will be norm of CV is mod C times norm of V, and that mod C is the absolute value on K. Okay, so all the norms with respect to that absolute value, if you define the norm, all those norms are equivalent. That's the first observation. So let's see why. We are going to give the proof as in Lang under one more assumption that K is locally compact. What is locally compact? What is locally compact?
Every neighborhood has a open neighborhood content in it whose closure is compact.
Yeah. Every point has a compact neighborhood. Every point has a neighborhood whose closure is compact. So assume K is locally compact. Standard examples will be R, which is a locally compact field. And QP is also locally compact. Which can I assert now? Okay, let me assert. Maybe I can't. Yeah. Anyway, we haven't really looked at QP, but it's also an example of a locally compact field. I can verbally say why so, because, for example, if you take the point 0, see these are fields, right? And addition and multiplication are continuous in the topology coming from absolute value. So in order to check every point, it's enough to check at the origin, because translation is continuous. Translation is actually homeomorphism, not just continuous. And so if you take the point 0, the origin, it has a neighborhood. You can, so just like, there are p-adic numbers, there are also p-adic integers, what is denoted by ZP, and that is a neighborhood of 0. And we will show later maybe that ZP is compact. So, and it's also open. So it has an open compact neighborhood. So that's also locally compact. Anyway, there are plenty of such fields. Assume K is locally compact, and we will give a proof that all the norms are equivalent. Result is true even without this assumption, and Lang says that his algebra, the textbook algebra, has a proof more generally, but we are going to deal only with these kind of fields, so we will give the simpler proof. Okay, under the assumption that it's locally compact, though it is true without this assumption. So fixed basis of V is finite dimensional, so some n, V1, V2, etc., Vn. And you have the standard sup norm. So what is a sup norm? If you take a vector in your vector space, expand it along this fixed basis, summation xi vi will be your arbitrary vector, where xi is a scalars. And the sup norm is the supremum of the absolute value of the coordinates. Absolute value is the absolute value on K, with respect to which it is complete. Okay. So this is the standard thing, right? So this essentially means with respect to this basis, it's a tuple, it's an n tuple. x1, x2, etc., xn. You take the absolute value of the xi and you take the maximum. Sup is same as max. It's a finite set. And you can check that this is a norm. This is a standard norm that you have seen. It's a sup norm with respect to this basis. And what we are going to show is that you take any other norm, we are going to show that that is equivalent to the sup norm. That's enough, no? In order to show that all the norms are equivalent, we are going to show that any norm is equivalent to the sup norm. And therefore, any two norms are equivalent. Because equivalence is an equivalence relation, right? So this is what we are going to show. So this is the definition of the sup norm. Sup norm with respect to this basis, we are fixing a basis. Okay, so if mod is, so sup norm I am denoting by double mod, 2 lines here. And if usual mod is any other norm on V, we are going to show that this is equivalent to the sup norm. So what do we have to show? We have to show that there is a constant such that mod of this vector is less than or equal to a constant times the norm of this vector, and the other way, norm of this vector is less than or equal to a constant times mod of this. Mod is also a norm. I'm just using the word mod of this vector. We have to show both ways. One way is easy. So you take mod of this, and at the end somewhere here I have to show that it's less than or equal to a constant times the double mod, the norm of this vector. So you have triangle inequality for this norm. So if you apply triangle inequality, you will get this is less than or equal to summation mod of xi vi. But mod of xi vi is mod xi times mod vi. What is this mod vi? This is the norm. And what is this mod xi? This is the absolute value on the field because xi is a scalar. Okay. Now mod xi is less than or equal to sup of mod xi by the definition of sup, and this is true for all I. So you can plug in that and take that out. So this is less than or equal to sup of mod xi, which is the definition of norm of this vector. This is sup of mod xi. That comes out, and what is remaining is summation mod vi. But summation mod vi is a constant, right? Because vi is a fixed basis. So this is a constant. So we have got modulus is less than or equal to a constant times this norm. So one way is shown. And now we have to show that this is less than or equal to a constant times this. Okay, so this is a constant times this. So one way is shown. For the next way, we are going to use the fact that our field is locally compact. So one observation from this inequality is, in particular, this function, this norm, is continuous with respect to this norm, right? Once you get this inequality, if there's a sequence which converges here, if xn converges to x in this, if xn converges to x in this norm, then of course xn converges to x in this norm because of this inequality. So this is continuous with respect to that norm. This function is continuous with respect to that norm. Since k is locally compact and v is finite dimensional, right? And this norm is what? This norm is just taking the tuples. So this is like v, you are looking at v as k power n. So that's also locally compact, right? Because if you have a compact neighborhood in each axis, you can take the product of all that. That's a compact neighborhood in v, right? Finite product of compact sets is compact. And that will be a neighborhood. And or if you want to say an open neighborhood whose closure is compact, all those will go through because of finite products, and therefore this is locally compact. And therefore, if you take the unit sphere, this is compact. Okay, so this is a compact set. X says that norm x is 1. This is a compact set. Basically, you know, you're using finite dimensionality. That's why you are getting this compactness. In an infinite dimensional non-linear space, the open unit ball or the unit sphere, these are not compact. But here it is true. This is compact, and therefore what can you say? Because this is continuous with respect to this norm. What do you know about a continuous function on a compact set? A continuous function on a compact set will attain its maximum and minimum. Right, extreme values. So in particular, it will attain its minimum. So modulus attains a minimum. This 1 bar modulus attains a minimum on the set. Say it might attain at many points, but at least at one point, let us say it attains its minimum at V. So what's the meaning of this? Mod of V is less than or equal to mod of X if norm of X is 1. It attains its minimum. V is such that mod V is less than or equal to mod X for any X in this. Is there a question?
Sir,
Yeah.
suppose if V is locally compact, does it directly imply that the unit sphere is compact? Like we did it in functional analysis, but here can we directly see it that if V is locally compact, then the unit sphere is compact?
I think that is also true. Yes.
So how are you concluding that? Like, is it something which we can?
Is it obvious? But it is certainly true that it's a characterization of locally compact spaces in your functional analysis, right?
Yeah.
So, and I think that is not very hard, so I didn't think about it. In fact, this is what you first show in order to show that locally compact nonlinear space has to be finite dimensional, right?
No, we showed that the unit sphere is compact if and only if the space is finite dimensional.
Yeah, but
we didn't really look into locally compact spaces in functional analysis.
Isn't this an ingredient in what you in showing that? When you
Sorry, can you repeat?
Isn't this an ingredient in showing that when you want to show V is finite dimensional if and only if it's locally compact if and only if it's finite dimensional? Is that straightforward? One direction is obvious, but the other direction there's some work, no?
Yeah.
And I thought I could be wrong because I haven't looked at it recently, but I thought this is what you need in order to show that. But I could be wrong. But anyway, this is a true statement. So let's fix it also. Maybe not in the class, but try to give a proof of this. That locally compactness is equivalent to either the closed unit ball being compact, which is equivalent to the boundary being compact. Okay, this is certainly a true statement, right, Manav? You agree with that? You're asking about the proof.
Yeah.
Yeah. So try to give a proof and let me know next time whether it requires work or it's kind of obvious. Do you see a proof right now? Then you can say that. If it takes time, then let us leave it.
Yeah, I'll think about it. I've forgotten a bit about that.
Yeah, I don't think it's much of a deal. But at this time, maybe we don't want to spend time on that. Okay, so the point is it attains a minimum. So there is a V. So mod V is less than or equal to mod X whenever norm X is 1. That's what we have. Now take any non-zero vector Y and write it as y1, v1 plus etc. yn, vn. This is a fixed basis, expanded along the fixed basis. And what do we know? We know that norm of y, what is norm of y? It is a supremum of mod yi, and supremum is maximum. So there is a j such that mod yj is the norm of y, right? These are finite things. So there is a j such that mod yj is norm of y. And therefore, what is the norm of y by yj? Norm of y by yj will be 1 by mod yj times norm of y, but norm of y is mod yj. So y by yj is a vector whose norm is 1. Y by yj is a vector here whose norm is 1. Why is my, yeah. So, okay, my mouse is not working right now, but yeah, it's a vector here, y by yj is here, and therefore you agree, right? Mod v is less than or equal to mod of y by yj. Why? Because it attains a minimum at v on this set, and y by yj belongs to this set, y by yj belongs to this set, therefore mod v is less than or equal to this, but this is equal to mod y by mod yj. Right, by the definition of the norm, yj is a scalar, so 1 by mod yj, this is absolute value, that comes out, and what remains is this modulus is this norm. So it is norm of y by mod yj. You get this, and therefore you get mod v times mod yj, but mod yj is norm of y. So mod v times norm of y is less than or equal to mod y. In other words, norm of y is less than or equal to a constant times mod of y. So you have got the other inequality. So what you have shown in this slide is any norm is equivalent to this norm, the sup norm. And therefore, any two norms are equivalent. Is the proof okay? Oh, by the way, I will put the slides on Moodle also. So the slides will be available on Moodle and the lecture video will be also there on YouTube. Or it might be there in MS Teams also, I don't know. But on YouTube, it might appear tomorrow or later because I'm not the one who's uploading it. Okay. So since this is complete, V with respect to this norm is complete. This is okay, right? Because what is this norm? This is supremum of all the absolute values. And if you have a Cauchy sequence in tuples, that's equivalent to Cauchy sequence in each of those. And since your field is complete with respect to the absolute value, this vector space is also complete with respect to this norm. Because it's just tuples, it's a standard thing. So this is complete. And we have just shown that any two norms are any norm is equivalent to this norm, and equivalent norms Cauchiness is preserved. So in any norm, V is complete. That's the conclusion. So because this is complete and any norm is equivalent to this norm, we have concluded that the vector space is complete with respect to any norm. Now, we are not interested in a vector space right now. You are interested in a finite extension of K. So this is a field which is a finite degree extension of K. So you can think of this as a vector space over K. And our conclusion is if you have fixed an absolute value on K and suppose you can extend it. I'm not saying that you can extend it. Suppose you have a way of extending it. Then we are saying that that extension is uniquely determined. So right now I'm not saying that you can always extend the absolute value. What all I'm saying right now is that if you can extend it only in one way. It's uniquely determined. And why is that? We have shown it already. Why? Because E is a finite dimensional vector space over K because it's a finite degree extension of K. So it can be treated as a finite dimensional vector space over K. And any two absolute values will be equivalent because an absolute value on E is a norm on E, and any two norms are equivalent. Therefore, any two absolute values will be equivalent, and equivalent is stronger than dependent. Therefore, they are dependent, and dependent meaning they will give rise to same topology. That's a definition, and they are positive powers of each other from the exercise that you are supposed to do. Okay, so they are positive powers of each other. So if you have two absolute values, then mod x1 is equal to mod x2 power lambda. But these are extensions of a given absolute value on K. So on K they agree. So mod x1 equal to mod x2 power lambda for all x in E. In particular for x in K. But for x in K, these two are absolute values are extensions of a given absolute value on K. So on K they agree, and therefore lambda has to be 1. Lambda has to be equal to 1. So since they coincide on K, they have to be equal. So that shows that any two absolute an extension of an absolute value is uniquely determined. So in particular, if you take an isomorphism of E over K, let us say sigma from E to sigma of E, so E to K bar, and let's denote the image to be sigma of E. If this is an isomorphism over K means what? It fixes element wise, K element wise, sigma of x is x for x in K. Then you have mod sigma alpha is mod alpha for every alpha in E. Why is that? Because if you have one absolute value on E extending K, then this defines another absolute value on E extending K, because sigma alpha is alpha if alpha belongs to K. So you get two absolute values extending the given absolute value, and they are equal. It's uniquely determined, and therefore you conclude that these two are equal. It's a corollary. Okay. Fine. A very basic example. So you've already seen an example which I said verbally, which is take rational numbers take a prime number and given any rational number, you can write it as p power r times m by n, where m and n are co-prime to p, where r could be 0, r could be positive, r could be negative. It's an integer which is 0 or positive or negative, whatever it is. Define the absolute value of that rational number to be 1 by p power r. You can check that all those inequalities are true. In particular, the ultrametric inequality is true. It's a non-Archimedean absolute value. And you can complete it, you will get a complete field with a non-Archimedean absolute value. You extend the absolute value also using the density. Okay, another basic example to keep in mind, that example is also part of this example. Let O be a discrete valuation ring. How many of you know what a discrete valuation ring is? Right now, not very important, but still, just to talk to you. Have you seen a discrete valuation ring in one of the algebra courses? Have you seen a local ring?
So like I saw the discrete valuation ring in the lecture.
Not very audible for me.
Yeah, now is it audible?
Yeah, now it's audible. Yeah.
Yeah, I have seen a discrete valuation ring.
Okay, do you recall the definition?
So a valuation ring is one where alpha belongs to K or alpha belongs to V or alpha inverse belongs to V for an extension field K.
Okay.
And for a discrete valuation ring, we define a valuation function from the ring to Z, from K to Z, a field to Z.
Yeah.
And we take the everything with the inverse of everything which goes to positive numbers,
Okay.
non-negative numbers.
Okay.
That gives us a discrete valuation ring.
Okay. That's one standard definition. And you might have seen that it's equivalent to, and you know what a local ring is?
Yes, just unique maximal ideal, right?
So from that perspective, a discrete valuation ring is a bit stronger than a local ring. The definition that you gave, one can show is equivalent to being a PID with a unique non-zero prime ideal. So a discrete valuation ring is a PID with a unique non-zero prime ideal. This will give rise to a valuation, and then it will coincide with what you said, Manav. So I have started with this definition, and how will you get the valuation? Valuation is another word for absolute value. In the sense, when you, yeah, if you have a non-Archimedean absolute value, that gives rise to a valuation. So it's like, exponential and log. Exponential is like the absolute value and log is like the valuation. So a PID with a unique non-zero prime ideal, let's say M is the non-zero. So if there is a unique non-zero prime ideal, then there's a unique maximal ideal, right? Because any maximal ideal is a prime ideal and there is always a maximal ideal. So this is an example of a local ring, but something stronger. So call it M, and then M will be generated by one element. Why? Because it's a PID. So it is singly generated. Let's say, so this is the notation pi, not the usual pi. This is in LaTeX what is called var pi, but I will call it pi. So M is generated by pi, and it's a PID, and every PID is a UFD. So everything you can write uniquely, you can factorize. So any element of your PID can be written as pi power r times a unit u. And in particular, anything in the quotient field of your PID can also be written as pi power r times u, but now r could be negative, depending on whether it comes in the denominator or numerator. So it's exactly like I define the valuation for Q, the periodic valuation, exactly like that. So U is a unit, it's in O star, and R is in Z. R could be negative also, depending on whether the denominator is divisible by pi or the numerator is divisible by pi. And you can choose any number between 0 and 1, any real number between 0 and 1, and you can define mod alpha to be C power R. So earlier when I defined the periodic absolute value, what was the C that I chose? Do you recall my definition of the usual periodic absolute value? What was my definition? Can one of you recall?
1 by P power r.
1 by
P power r.
Yeah. So what is my C there? What is this C between 0 and 1? 1 by P. 1 by P. 1 by P power R. Right? So the standard normalization in that one standard normalization is to take C equal to 1 by P, which is very useful. Okay, but you can take any C between 0 and 1, you can show that this is an absolute value. And you can show that the ultrametric inequality is true. Mod x plus y is less than or equal to maximum of mod x comma mod y. So please check these things. So show that this is a non-Archimedean absolute value. Okay. Now let us do the Artin-Vapers theorem. It's an analog of the Chinese remainder theorem, which you have already seen. Can you quickly recall the Chinese remainder theorem?
Product of prime ideals is equal to their product of powers of prime ideals is equal to their intersection.
Yes, but more classically, how will you? No, that's not the theorem. No, is that the theorem? Yeah, okay, that's a consequence. Yeah, so standard Chinese remainder theorem, that's a consequence of that. So you will say that if I and j are, okay, instead of 2 you can do it for finitely many. If I and j are ideals which are co-prime, what does that mean? When do you say two ideals are co-prime or relatively prime to each other?
Is it the same as co-maximal?
What is the word they use? Co-maximal, is it?
Yeah.
Yeah. So what is the definition of co-maximal?
I plus j is equal to the entire ring.
It's called co-maximal, is it? So I said co-prime. Yeah, maybe it's called co-maximal. So if I plus j equal to r, then r mod ij is isomorphic to r mod I cross r mod j, right?
Yes.
Yeah. So this is Chinese remainder theorem. So in classically, how do you say this for integers? What is the real Chinese? Right. This is maybe in BC, sometime BC or something long back. So how do you formulate this? It's a surjectivity which is important, and what it means is if you have A and B co-prime, and then you can always find, right? You want to say that Z mod A cross Z mod B is isomorphic to Z mod AB. So you want to say that given, yeah, so let's say Z mod M and Z mod N. So if you want to say that if A and B are co-prime, and then you can solve for the congruences. X is congruent to A mod M. Right, you take something in Z mod M cross Z mod N. So let's say A comma B belongs there. Then you want to show that there exists something in Z mod Mn. So you can get an X which is A mod M, which is B mod N. Right? You can get an X which is right. What's the map from R mod I cross R mod J and R mod Ij? What is the standard map? Natural map. Yeah. Which way is the surjective? What is the standard statement? Which way you formulate, and then the surjectivity is the important part, right? So you want to show that. Yeah. So R mod Ij to R mod I cross R mod J, there is a natural map, no? X plus Ij going to X plus I comma X plus J, right? That's the natural map, and you're showing that this map is surjective. So if you give X comma Y, then I can get a Z such that Z is Z is congruent to X and Z is congruent to Y. I can solve for this. So this is the Chinese remainder theorem, and this is an analog of that. What we are going to do, what is called the Artin-Vapers result. You will see the analogy. So this is dated 1945. Yeah, so this is one thing, which is striking compared to, let us say, we are doing complex analysis or something, or some kind of analysis. If we do, most of the results that we have in the course will be a bit more older, right? I mean, if we are doing complex analysis or real analysis or functional analysis, something, most of the time we will be talking about Weierstrass and Cauchy and those kinds of mathematicians. Whereas you will see that the years coming throughout this lecture are slightly more modern. I mean, 1945 is not modern, but yeah, relatively. So this is 1945 and is due to Emil Artin and George Vapers. Emil Artin is a very, very famous mathematician, one of the most important number theorists of the 20th century. Have you heard Emil Artin, the name, before?
Yes.
Yeah, who has heard Emil Artin? I am surprised.
The father of Michael Artin.
Okay, so you know some history, yeah. Michael Artin, all of you know because of his famous book Algebra. Emil Artin is Michael Artin's father. Yes, yeah, good. So very, very, very famous number theorist. There is what is called class field theory, which is an advanced part of algebraic number theory, and I think it's most of class field theory is due to him, Emil Artin. Okay, so let's take this. It's not very difficult. So let us say that pairwise independent absolute values are given. What is independent? They are not dependent. They don't generate the same topology. So any two of this you take, they generate different topologies. Okay, so pairwise independent absolute values. This is like your Chinese remainder theorem, right? You have given finitely many ideals which are pairwise co-maximal. I1, I2, In are such that II plus Ij is the full ring, pairwise co-maximal. So this is similar to that, pairwise independent absolute values. And suppose you have finitely many elements in K. So in Chinese remainder theorem also it's similar, finitely many elements are given. And then Chinese remainder theorem says that there exists an X such that X minus Xi belong to your ith ideal. You can simultaneously solve all those congruences. Here's something similar. For any epsilon positive, there exists X in K. So this is like solving the congruences together. There is an X whose distance from Xi in the ith absolute value is less than epsilon, and this is simultaneous for all I. Okay, is the statement clear? So it is reminiscent of the Chinese remainder theorem, which would say that given finitely many these things, there is an X which will solve all the congruences simultaneously. And this is similar for any epsilon, there is an X. For any epsilon, there is an X depending on epsilon, such that the distance in the ith absolute value, the distance from the ith element in the ith absolute value is small. Okay, so this can be done. So let's do a quick proof of this. I'm going to do this for 2, and then I'm going to prove a statement for 2 absolute values, and then I'll prove a similar statement for finitely many absolute values, and use that statement in order to prove the theorem. So this is the Artin-Vapers theorem. Okay, so since take any 2, let us take mod 1 and mod s. These are independent, so they don't generate the same topology. So what can you conclude? You remember that statement that I quoted and asked you to prove at the very starting? I said that what you should prove is if mod x1 less than 1 implies mod x2 less than 1, then one is a positive power of the other. Right? That's what I asked you to prove. So, and if they are positive powers of one another, then they are of course dependent. So since these two are independent, one cannot be a positive power of the other, and therefore it cannot be true that this statement is true. Right? Earlier I asked you to prove that if this statement is true, then one is a positive power of the other, which will imply that they are dependent. Therefore, because they are independent, it is not true that this implication is true. And what does that mean? There is an alpha with mod alpha 1 is less than 1, and mod alpha s is bigger than or equal to 1. There is at least one such alpha, because this is not true. Clear? Similarly, there is a beta such that mod beta s is less than 1 and mod beta 1 is bigger than or equal to 1. Now, if you take beta by alpha, it has the property that, what is the property of beta by alpha? What is modulus 1? Mod y of 1 will be mod beta 1 by mod alpha 1, and mod beta 1 is bigger than or equal to 1, and 1 by mod alpha 1 is strictly bigger than 1. Therefore, mod y 1 is strictly bigger than 1, and similarly mod y s is strictly less than 1. So I've got both strict. 1 is strictly bigger than 1, and in the s absolute value it is strictly less than 1. This is the claim that I conclude because of independence. Okay, now I'm going to make the claim that there is a z in k such that in the first absolute value it is bigger than 1, strictly bigger than 1, and in all other absolute values 2 to s, the modulus is strictly less than 1. So for j equal to 2, we have already proved this, right? If you have two absolute values, then I can choose an element. Mod 1 is strictly bigger than 1 and the other modulus is strictly less than 1. Now I'm extending it to a finite number. In the first absolute value, it is strictly bigger than 1, and all other absolute values, it is strictly less than 1. Proof is by induction. N equal to 2 is already done, and assume up to s minus 1. Assume there is a z such that mod z1 is strictly bigger than 1 and mod zj is strictly less than 1 up to s minus 1. We have to show for up to s. We have to exhibit an element. So consider mod z power s. You have got such a z by induction hypothesis. Consider its sth absolute value. Suppose it is less than 1. Then of course you are done, right? Then that z will do the job. If it is equal to 1, if mod zs is equal to 1, what you do is you consider z power n y. And you may have to take a large enough n, and this will do the job. Why is that? Because mod z power n y, mod 1, the first absolute value, mod z is bigger than 1. What is this y? This y is the y that we have got here. This is the y. So mod y 1 is bigger than 1. So if you take mod z power n y, if you take mod z power n y, mod z is bigger than 1, mod y is also bigger than 1, therefore this is also bigger than 1. So the first part is true, and this part for the last sth one, this is true because mod z is 1, but mod y is strictly less than 1, therefore modulus of this is strictly less than 1. And what about all these intermediate one, 2 to s minus 1? Mod z is strictly less than 1, but mod y you don't know. Mod y you don't know. Mod y may be some positive number, but depending on that positive number among all these finitely many things, you choose n large enough. Because mod z is strictly less than 1, mod z power n will tend to 0. So choosing n large enough, you can make this full modulus less than 1. So this will do the job. You may have to take large enough n depending on mod y for these absolute values. Is the argument clear? So this will give you that if mod is 1. If mod is bigger than 1, then what do you do? Then you have to do one more trick. Of course, you know, this kind of proofs, if someone tells you what the proof is, then of course it is easy. But the ingenuity is in coming up with this, which of course they have done. So we are just repeating. So, sorry. If mod z is bigger than 1, then you consider this sequence, z power n by 1 plus z power n. Call it Tn. What do you observe about this sequence? Let us see where this sequence converges in various absolute values. So if you take this sequence, can you tell me in the first absolute value what is the limit? First absolute value meaning mod 1. What is the limit? Right, this is a sequence. No, as n varies, this is a sequence. What is the limit in the first absolute value?
1.
Why is that? Because it is 1 by z power n plus 1, and 1 by z power n converges to 0. So the limit is 1. Very good. And what is the limit in the sth absolute value? Again 1, because mod z s is bigger than 1. Right? And what is the limit in all the other absolute values?
0.
0. So conclusion is this tends to 1 in absolute value. So I am using Lang's notation now. Instead of saying it in words, he uses the word V for absolute value, valuation. Okay. For a non-Archimedean absolute value, he uses the word valuation. So in absolute values V1 and Vs, instead of saying first absolute value S the absolute value, I can just write V1 and Vs. It tends to 1, and in all other absolute values it tends to 0. That's fine. And now what you do is take the sequence T and Y, and depending on Y you may have to take large enough N, and this will do the job. Let us quickly check it. What is the first absolute value for T and Y? Because mod Y is bigger than 1 and Tn tends to 1. Tn tends to 1 and mod Y is bigger than 1. So for large enough N, mod T and Y is strictly bigger than 1. So that part is okay. And in all other absolute values, you want it to be strictly less than 1. So what happens in the last absolute value? Last absolute value, mod Y is strictly less than 1 and Tn tends to 1. Therefore, this whole thing absolute value is strictly less than 1 for large enough N. And in the middle cases, what will happen? Middle cases Tn tends to 0. Right? In these cases, Tn tends to 0. So depending on Y, if you go large enough, mod T and Y will be strictly less than 1. So therefore, you have proved this claim. You have proved this claim that there is an element Z such that the first absolute value is strictly bigger than 1 and all other absolute values are strictly less than 1. And using this claim, we will finish the proof. So choose that element Z as in this claim. In the first absolute value, it is bigger than 1, strictly bigger than 1. In all other absolute values, it is strictly less than 1. Choose such as Z and consider this sequence Z power n by 1 plus Z power n. The argument that you have given earlier, what do you know about this sequence now? This sequence converges to 1 in the first absolute value and converges to 0 in all the other absolute values, right? Because in all other absolute values, mod Z is strictly less than 1. So it converges to 1 at V1 and tends to 0 at Vj for all the remaining j, 2 to S. And therefore, the conclusion is there exists a Z1 which is very close to 1 at V1 because it tends to 1 at V1 and tends to 0 at Vj. So there is a Z1 which is very close to 1 at V1 and very close to 0 at Vj for all j not equal to 1. You agree? You are interested in this sequence. In the first absolute value, it converges to 1 and in all other absolute value, it converges to 0. So you can pick an element which is sufficiently close to 1 as you like. Whatever epsilon is there, close to 1 in that epsilon and close to 0 in that epsilon in the rest of the absolute values. Agree? And this you can repeat not just with the first absolute value, you can do this with the second absolute value, you can do this in the third absolute value, etc. Therefore, similarly for each I, you get a Zi which is very close to 1 at the ith absolute value and very close to 0 at all the other absolute values, j not equal to I. Because whatever we proved here till here, you can apply for all other I, and therefore you have got elements like this, and now you are done because you can take this element now. So in the claim is that there is an x with some property mod x minus xi in the ith absolute value is very, very small, less than any epsilon, arbitrarily small. So if you take the linear combination of xi's are given to you, right? What is given to you is xi's, and you have to get an x such that x minus xi is small. So if you choose these zi's and if you take the linear combination, what happens? What happens at I now? In the ith absolute value, xi goes to zi goes to 1. Zi goes to 1 in the ith absolute value. Therefore, zi xi goes to xi. And all other zi, zj goes to 0. Therefore, x goes to xi. So x minus xi is small in the ith absolute value. This will do the job. Is the proof clear? Okay, you may have to go through this once again. So I'm giving a specific x which will do the job. This x has a property. This x has the property that this, because it was a linear combination, and zi goes to 1 in I and zi goes to 0 in all other absolute values. Therefore, in the combination, summation zi xi goes to xi in I, and that's what we wanted. So this is a result due to Artin and Webers. Okay, so I think I'm coming to the end of today's lecture, but I will just introduce these words, Hensel and Krasner. So there are two important lemmas which we will do next time about non-Archimedean complete fields. One is called Hensel's lemma and the other is called Krasner's lemma. Okay, Hensel and Krasner. So Kurt Hensel is a very famous German mathematician, 1861 to 1941. And he is the one who invented or discovered, or I don't know the word in mathematics, who introduced periodic numbers. So people say, so I was reading the Wikipedia page for periodic numbers. Apparently, ideas like this was there even earlier in the work of Dedekind and Kummer and all that. But he is the one who actually introduced this notion, and it appears in one of his works in 1897. Okay, and this was a surprise, these kind of numbers, which are very useful in usual number theory. You will see that in this course, how these numbers, periodic numbers, are useful in studying ordinary numbers. Okay, so he introduced this in 1897. This is the most basic example of a non-Archimedean complete field. So now you know what periodic numbers is. It was not part of my slides, but I put this periodic absolute value on Q and I completed with respect to that. And one of you asked this question, is this a field? I said you should check that it is a field, and then you can extend this absolute value to that, and it is complete with respect to that because you had completed. So so it's the most basic example of a non-Archimedean complete field, and that is Kurt Hensel. And versions of Hensel's lemma, which I'm going to state in the next slide, they date back to his original papers. So a paper of 1904 has a version of Hensel's lemma. Slightly more general version is there. He published a book called Algebraic Number Theory in 1908, and Hensel's lemma is there. So it is from early 1900s. Mark Krasner was a Russian mathematician, but who emigrated to France long ago when he was very young. So he is a French mathematician, Russian born, and he had a lot of trouble in World War and all that. He had to hide and he had to serve in the military and all that. I was reading about Mark Krasner. He's not that famous as Hensel, but a very famous mathematician nevertheless. Kind of modern. He passed away only in 1985. And Krasner's lemma appeared in a paper of his in 1937. By the way, Krasner's lemma is very simple to prove. We could have proved today itself. It requires only what we have already done earlier, that all the norms are equivalent. That's all that you need. Hensel's lemma is also not very difficult. It is something like what you call Newton's method in numerical analysis. Some algorithm is there which will produce, whatever element you want. Let's just state those two lemmas and stop there. So K is a non-Archimedean complete field. An example to keep in mind is QP, the field of periodic numbers. And a very complete non-Archimedean field has what is called its ring of integers. So QP has ZP. So what it is you have an absolute value, right? You take modulus less than or equal to 1. You can check that this is a ring. Why is it a ring? Because of your ultrametric inequality. Right, you have to show that x plus y is also there, but modulus of x plus y is less than or equal to maximum of mod x comma mod y. So if mod x and mod y are less than or equal to 1, then mod x plus y is also less than or equal to 1, and mod xy is also less than or equal to 1. So it's a ring, and this ring, it's called its ring of integers. And this ring has a unique maximal ideal, making this ring a local ring, and it is given by all those x. So sorry, I should have taken x in O. Well, it doesn't matter. X in K also is same as x in O. X in O says that mod x is strictly less than 1. Why is this the unique maximal ideal of this ring? Because in order to show that it has a unique maximal ideal, it's enough to show that the complement of this in O is a unit. And that is true, right? What is the complement of P in O? It is x such that mod x equal to 1. But if mod x equal to 1, then x is a unit, right? because x inverse also has the same property, right? If mod x equal to 1, then mod x inverse is also 1. So x inverse also belongs to the ring, so x is a unit. So anything outside this, the complement of this consists of units, making this a unique maximal ideal, making this a local ring. So this is Hensel's lemma, just a statement, proof will be next time. So if fx is a polynomial, where are the coefficients from? Coefficients is from your ring of integers. Okay, so you have a complete non-Archimedean field K, you have its ring of integers, and suppose you have a polynomial with coefficients in O, from OX if you have a polynomial, and suppose you have an element of O such that this identity is true. You evaluate f at alpha naught and take the absolute value. What is f prime? F prime is a formal derivative. If you have x square plus ax plus b, then 2x plus a. Just take derivative, formal derivative. And that's another polynomial in degree less. And you evaluate that at alpha naught and take the modulus and take the square. And suppose this condition is true. There is a point alpha naught such that modulus of f of alpha naught is strictly less than modulus of f prime alpha naught square. Then the lemma says, in fact, it's constructive, it's an algorithm. So Hensel's lemma is this algorithm. You can form this iterative sequence. Starting with this alpha naught, you can take alpha 1. From that alpha 1, you can make alpha 2, etc. So what you do is take alpha I minus f of alpha I by f prime of alpha I. Do this. I'm quickly getting a doubt whether this statement is correct or not. Let me just double check this. Okay. Anyway, we will do the proof, but let me just check this statement. You can see the screen, no? Manav, can you confirm?
Yes.
Yeah, so let us just check the algorithm is, yeah, this is what I'm saying, right? I don't know whether you can see that. Is the font big enough? This is what I have written, no? Rk plus 1 is Rk minus f of Rk by f prime of Rk. So that's correct, yeah. No, I got confused because here there is a square and here there is no square, but this is correct. We just double checked, and in the proof anyway it will be clear. So this sequence, and what about this sequence? So you have got a sequence of numbers from, you've got a sequence of numbers. Am I saying the sequence of numbers is in O? I am not saying that. Alpha naught is in O, but while doing this I could be in K. K is the quotient field of O. I could be in K, but I have got a sequence, and the claim is that this sequence converges in that absolute value, and it converges to a root of f of x. So Hensel's lemma is about getting a root of this polynomial. So if there is an alpha naught, then there is a constructive way of getting a root of this polynomial, and this root alpha is actually in O. Okay, so it's a very important lemma. It's not very difficult, but it's very, very important, very useful lemma. And it says that if there is, so this is all that you need. There is a point in O satisfying an inequality. Then here is a way of constructing a root of that polynomial. The root is actually in O. In between, the elements of sequence need not be in O, but the limit is in O. Okay, so it establishes a root in O of polynomials. So, in order to get roots of polynomials, a very useful lemma works over complete non-Archimedean fields. Moreover, you know that the starting point alpha naught which you had, and alpha, this distance is less than or equal to this quotient, f of alpha naught by f prime alpha naught square. So in particular, this distance is strictly less than 1, right? This distance is strictly less than 1 because this is strictly less than this, therefore this is strictly less than 1. This is Hensel's lemma. Okay. So once I stop the lecture, maybe we have 5 minutes to chit chat, and I will give you an example. It's how useful this is. So for now, just remember the statement. Okay, it's very easy to construct nice examples. Since I haven't written it in my slides, let's verbally discuss this soon after the lecture. Okay, so just ask me. If I forget, just ask me. This is Hensel's lemma, and let me also state Krasner's lemma. So K bar is an algebraic closure, fix an algebraic closure K bar, and if alpha is from K bar, which means alpha is algebraic over K, its conjugates, its Galois conjugates, let us denote by alpha 2, etc., alpha n. It's distinct alpha conjugates. Okay. So what is the meaning of a Galois conjugate? If alpha is in K bar, then you can take various automorphisms. Sigma, yeah, so you can take the minimal polynomial of alpha and the other roots, right? In other words, you can take sigma from Galois group of K and you take sigma of alpha. And they will be finitely many distinct conjugates. So alpha 2, etc., alpha n. And then Krasner's lemma says that if beta is algebraic over K, beta is in K bar, is such that such a strict inequality is true. The distance between beta and alpha is strictly less than distance between alpha I and alpha for all these other conjugates. Right? The other conjugates, I going from 2 to n, alpha 2 to alpha n. So if beta is closer to alpha than all the other conjugates of alpha. So you have all these other conjugates and look at this distance, and if beta is closer to alpha than this, then the lemma says K alpha is contained in K beta. Okay, so the field generated by alpha over K, the smallest field containing K and alpha, this field is contained in K beta. This is not very difficult. All norms are equivalent is enough to show this. We will show it next time. So this is Krasner's lemma. Very simple lemma, but extremely useful lemma. Okay, so we will see these two lemmas, the proofs of it next time. And I will stop here. And we have, okay, so strictly speaking, the time is up. Do you have another class? Anyway, let me stop the recording. And let me stop the screen sharing. Stop sharing. And also stop the recording.